Today we're going to talk about the greatest experiment. This is Unit 6 in the lecture series, and the title is The Greatest Experiment. What we're going to be talking about is the double slit experiment, which is generally considered one of the most venerable, formative experiments ever devised in physics. Before the 1800s, or even into the 1800s, light was considered as comprised of what they called corpuscles, essentially individual packets of light. That's what it's always was considered. I'm not sure that there was ever a good proof to demonstrate that fact, but it was generally believed that that was the case. In 1801, a scientist by the name of Young devised an experiment where he shined light through a metal plate with two slits in it, and by analyzing the way the light was divided and could be recombined, he determined, and we're not going to even try to get into the reasoning here because I don't think it's important, but he determined that light was a wave and not comprised of particles. So that was a big deal, and that's what the double slit experiment did. Turns out that the double slit experiment would be used many times going into the future to do further analysis on light and to try to learn more about its properties. And once again in the early 1900s that was done, and in 1909 some experiments were run that it proved just the opposite, proved that light is also comprised of particles. And so we really came up with what in physics they refer to the wave-particle duality of light. All interesting stuff, but not incredibly informative or helpful to what we're trying to accomplish in our discussions. But throughout the years, throughout the decades, multiple types of experiments were run by various physicists to prove various aspects of light's characteristics. In 1924, they were able to emit single electrons through these slits. And I believe actually that's when the wave-particle duality proof was done. But still there was one last thing to understand, and that thing wasn't really understood until the 1960s or 70s. And so the double slit experiment we're going to talk about is the most modern version of it, and we're going to get right into it in a second. One of the reasons that this is so interesting is, first of all, it has tremendous implications for science and for quantum theory. But second of all, this experiment really straddles the scientific and what some people might consider the metaphysical, because it talks about characteristics of matter and characteristics of reality that don't conform at all to sort of traditional reductionist or materialist principles. You'll understand a lot more about that as we go forward. These principles have been well known certainly since the 60s or 70s. Wave-particle duality for a lot longer than that, but certainly since the 60s or 70s, that there is this aspect to matter that relates to quantum theory. And so that was 35, 40 years ago. And still, as far as I can tell, typical high school science classes don't teach any of this. And I'm not sure that even early college teaches these principles, which is really crazy. But I think it's because these principles undermine some aspects of science, and these are inconvenient principles to consider because it really opens up giant new avenues of possibilities as to what makes the world work the way it does, and that's kind of inconvenient for modern science. So we'll kind of leave it at that, and we'll dig right into it. Particle versus wave behavior. Well, let's talk about just wave behavior just in general and particle behavior in general before we get into the experiment. By the way, the reason I'm kind of leaving this space open here is I have some figures that I want to show, and normally I'd use a whiteboard, but that's not really going to work right this minute. So hopefully you can see the sketches that I've made and we get the ideas across sufficiently. Let's talk about waves for a second first. What are some of the characteristics of waves? Well, once you initiate a wave, let's say you drop a pebble in a pond, that wave tends to propagate in all directions. Okay? And so that's one of the characteristics of waves. The other characteristic of waves is, and we'll demonstrate this a little bit so you can really see it, so it'll make sense to you. But if you take two waves and you take a look at the way they interact, what you'll actually find is waves are additive and subtractive. They actually combine very nicely. So if you have two waves and each one is 6 inches high and they're moving toward each other, where they meet, they'll be 12 inches high. And maybe if a 6-inch high wave meets a 6-inch low trough, you'll actually see flat, still water where the two waves cross. So waves can be combined in an additive or subtractive way, which is a typical property of wave. And you can kind of imagine imagery of a wave. It's very, very different than the definitive imagery of a particle. A particle has specific boundaries and specific size, weight, etc., and has a particular location. Whereas waves are constantly moving. One of the characteristics of waves is motion. All right? So lots of differences. And of course, particles, I don't think we need to get into all the kinds of attributes of particles. We deal with material objects every day, and particles are simply a material object. They have a size, they have a weight, they have a speed, they have a momentum, they have a location. And unless acted upon, those things don't change. So if a particle's location is at a particular place and its speed is 0, if you come back and look at it later, unless it's been acted upon, it'll be still sitting in that same place. All right? So that's particle versus waves. Very often, people talk about particle behavior. Newton, when he talks about particle behavior, you really kind of think of them in terms of billiard balls in a lot of cases. And some people actually use the term billiard ball universe to really get to the sort of materialistic kind of view of the universe, that the universe is this giant clockwork mechanism that is comprised of particles, and these particles act on each other. They bang into each other, and they end up doing things. So every chemical reaction, every time you have one particle and another particle interacting in some way, as I said, in a small sense, in a small scale, at the atomic level, these things are chemical reactions. But in the very large scale, maybe these are, galaxies crashing into each other. So, there's a general sense, if you go all the way back to Isaac Newton, that's sort of traditional materialistic science, is that all things are comprised of these particles interacting. Now, in the last couple hundred years, we've had tons and tons of advancements that have moved science beyond traditional Newtonian view of the world. But in many ways, a lot of people, even very, very technical people, scientific people, still deep in their gut, they view the world as a clockwork mechanism and as a bunch of Newtonian reactions. And we'll get into some examples of that as we move along. Okay, so let's just go through a few images here just to sort of get a baseline. So if you throw a pebble in a pond, this is the kind of thing you're going to see. You're going to see waves radiating out in all directions. Now we have a pool with 4 walls on it. We're going to see that if we throw the pebble in the middle, we're going to get these waves radiating out in all directions, as we've already discovered. But these waves are interesting. They'll actually bounce off the walls, and they will move back in the direction of the original wave, or in various different directions. Interesting thing is these waves interact with each other. What we're seeing here is an interference pattern, and if you go outside, take a look at a puddle in the rain, you will see these various different waves all radiating in various directions, and you'll see how the waves interact. And the way they interact is there'll be high spots and low spots. It'll be the arithmetic combination of all these waves at any point in the puddle, or in this case, the pool. So that's what an interference pattern would, that's an example of an interference pattern, is how these waves all sort of combine with each other. Now, let's take that pool and let's put a board across the pool. And really what I've got here is 2 figures, and so I might cover up the top figure and look at the bottom figure, and what you'll see is a board going across the pool, waves on the bottom going up to the top, and then waves propagating out from a little hole in that board. All right, and that's the way the waves will propagate. They'll really propagate in arcs coming out of that hole. And I've got a second board with another hole in it, and I'll actually show you the whole picture. We've got a second board with another hole in it that you can look at where you've got a wave and it's propagating out. It's exactly the same as this lower picture. These are two different pictures with boards with holes in two different locations. I'll show you why I'm doing that now. So now if we take those two holes and we put them in a single board, what you actually find is you're going to get waves propagating in an arc around this hole and another set of waves propagating in an arc around that hole, going out in this part of the pool. And what you're going to see here is, and it's very hard to draw, is you'll see an interference pattern emerge on this side of the pool. And if this pool had a wall against the back, and you were, let's say it was a glass wall, and you're standing on the outside of the pool looking back into the pool through the glass wall, you would actually see the interference pattern on the back wall where there'd be maybe a high part of the wave here right between these two holes, and then you'll see a low spot, and then you see another high spot and a low spot and a high spot, and so you'll see these peaks and valleys like these stripes of peaks going across that back wall. That is indicative of an interference pattern. Okay, so this is what two holes in a board with energy coming in this direction and the energy emitted on this side of the board in the form of two waveforms. All right. So that's what traditional waves would look like. And again, the whole idea here of the double slit experiment is to kind of look at as we were talking about earlier, the wave-particle duality of light. So we need to understand waves, we need to understand particles, and then we can take a look at this duality. All right, so let's take a look at particles now. And so what we want to do is we want to have a bunch of particles and a couple of different slits to shoot the particles through, because this double slit thing is important, and you'll see why in a few minutes. So what we're going to do is the analogy we'll use is a paintball gun, right? So a paintball gun, every time you pull the trigger, you're going to get a paintball shooting out of the gun. Or if you hold the trigger, it'll rapid fire. And so what we've got is we've got a paintball gun here shooting paintballs against the wall. And this gun is a little bit erratic, and so you're never really sure where that paintball is going to end up. It kind of moves around, up and down, back and forth. But it's going to give you a pattern on that wall that's somewhat of a random distribution, but it's a cluster around a central point, which is where the paintballs are shot at. Okay? So that's what your paintball gun is going to do. Now, if we create a screen here with a slot cut in it, and I show the paintball gun very close, but that's only because my drawing's not wide enough. Imagine this paintball gun way back, quite a ways away from this target. Every time you shoot a paintball, you may hit the target, you may go through the slot. You never know where exactly that paintball is going to go, but some percentage of those paintballs are going to make it through this tiny little slit. All right, and those paintballs that make it through the slit are going to hit the back wall, and guess what? It's going to make a shape here that's the same, similar shape as the slit, because every paintball, once it gets through the slit, is going to travel in a straight line and hit the back wall. So you're going to see a slit-shaped pattern on this back wall. All right? And all those random other paintballs that didn't get through the slit, well, they're going to hit this screen. They're never going to get to the back wall. All right? So you've got a slit, and then you have a slit-shaped pattern on the back wall. Well, now what we're going to do is, let me get this thing right here. We've got a double slit. So we've got a screen here with two slits cut in it. And the paintball gun is shooting paintballs, and they're hitting all over this screen. Every once in a while, one's going to go through the right slit, and every once in a while, one's going to go through the left slit. The ones that go through the right slit are going to hit in a pattern like this. The ones that go through the left slit are going to hit in a pattern like that. No surprises. This is the way the world works, as far as you know. Things are going to change here in a minute, but we'll get to that in a second. So, well, let's pause right here. So what we've done is we've taken a look at a wave, and we see what a couple of waves look like and how they behave when you send them through a couple of holes or a couple of slits, and how they interact on the other side, and the fact that they create an interference pattern. Then we took an analogous setup with, instead of a wave, with a gun that shoots particles. And we've shot those particles at a target that had a couple of slits in it. And every once in a while, a particle would go through the right slit, and every once in a while they would go through the left slit, randomly. And the pattern that we see on the back wall is the same shape as the slits cut in the target. This is all predictable stuff. This is exactly the way, things work, this is exactly the way things work for large particles. But now what we're going to do is we're going to scale this thing down, and we're going to look at small particles, and we're going to see how small particles work. Well, okay, so first of all, what we've done is we've already seen what small particles behave like when we did the double slit experiment using light. And what we've seen is interference patterns happening, but we also know that light is also particles. And what we're going to now try to do is see if we can really eliminate the wave aspect of light a little bit here, and really kind of focus on the particle attribute of light and see how that behaves at these very, very small scales. So what we've done is we've got a laser beam here. And this is what was done in the 60s and the 70s. And, this was done many years ago before then with very, very dim light sources and whatnot. But I think it's simple to let's just talk about lasers, because it's just a convenient test setup for us to discuss. So if we take a laser and we shine it on this back wall, it's simply, and this laser is not perfect. It's not at a subatomic level. Every single one of these bits of light is not going to hit exactly where the last bit of light shown, because our apparatus is not that accurate. You're going to get some diffusion. You're going to get some variation as to where these little particles of light hit. And so you're going to see something that looks very much like what you saw with the paintball gun. You're going to see a pattern, and the pattern's just going to be sort of a random distribution around a central point. Well, now let's create the same slit device and shine the laser at this target. Again, imagine the laser beam is further back, and imagine the laser is really illuminating this entire target. Individual packets of light are occasionally going to go through the one slit, and they're going to end up on the back target. And guess what? They're going to create a pattern just like the paintballs created. A lot of photons of laser light are going to hit this target and are going to be blocked completely. But the photons that pass through this slit are going to create a shape like that on the back target. No surprise yet, but now it's time to wake up and pay attention, because this is where the surprise happens. Okay, we got the exact same setup we did with the scatter gun, with the paintball gun. We've got a target here, this front screen, I guess we'll call it target. It's got two slits in it, and we're illuminating this entire surface with laser light. And occasionally, a packet of laser light is going to hit the target and just bounce off or be absorbed. Occasionally, you're going to get a packet of light that goes through one slit, and occasionally you're going to get a packet of light that goes through the other. Here's what happens, though. If you take a look at the pattern here on the back wall, you'll see that the area behind the slit, I've got a little oval here with a question mark in it. Nothing is going on there. We've got no impacts of laser light into that area. Side, same thing. No impact, or very few impacts of light. But look at this. In the center of these two, where the slits should be, where the light should be hitting behind the slit, we actually see a lot of impacts here in the middle. And then we see some out here. And then we see some more out here. And notice the striped kind of configuration of these impact areas. Well, it's not an accident they're striped. Remember, that's what we said you would see if you see an interference pattern. So what we're seeing in this experiment is that the packets of light coming through the right, randomly coming through the right slit, and the packets of light randomly coming through the left slit seem to be interfering with each other and combining in some way, in some kind of a way that as waves do, right? And it's illuminating or creating an interference pattern on that back wall. Well, that's kind of interesting. But what's kind of strange is when you shine light through one side, it creates they act as particles. When you shine it through the other side exclusively, they act as particles. But when you uncover both of the slits, all of a sudden everything starts acting as a wave. That's very interesting. So, of course, then it was up to the engineers and the physicists to figure out what was going on. So what they decided to do is you can control laser light to a very high degree. You can turn down the intensity of a laser light to the point where you can get individual packets of laser light, individual photons going through and hitting that back target. In the old versions of the test that happened in the 1800s and the 1900s, early 1900s, they used film typically, some sort of a photosensitive material like film, and they shot, particles, light particles or X-ray or those kinds of particles at the film, and every time it would hit the film, it would make a little light spot. In more modern test setups, they use a photodetector, but it's the same idea. The interesting thing about a photodetector is with an amplifier connected to it, you can run it to a speaker, and so every time any light hits the photodetector, it can make a click. And so if you have the laser on high intensity, you'll get just a static sound with all these millions and millions or billions of clicks happening. But if you turn the intensity of that laser down, 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 you can get to the point where you have individual photons being shot at the target, at the double slit target. And just if you take that double slit target away and just turn this thing down, you can and you listen to the speaker, the photodetector speaker, you're going to hear click, 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 click. You're going to hear individual clicks as each packet of light hits the photodetector. By the way, the idea here is these packets of light are quantum units of light, hence the name quantum physics. They're quantum units of light. They come in quantum pieces. It's kind of like a six-pack of beer. It comes with 6 beers. It doesn't come with 5.5 beers. It doesn't come with 3.5 beers. It comes with 6. Or maybe if someone took one of the beers, now you have 5. And if someone takes another one, you have 4, right? And so the quantum unit of beer, when you're talking about 12-ounce cans of beer, the quantum unit is a 12-ounce can, right? Well, the quantum unit of light is a photon. And so that wasn't always realized, but it's something we discovered. And it's kind of odd because we originally thought light came in packets, then we thought it came in waves, and now we understand it comes in packets that occasionally behave as waves. So we've kind of learned a lot as we go through the years of scientific advancement. So we turn this intensity of the laser down until we have a click, 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 where we have a photon, photon, photon. And then we put that screen back in front that's got the 2 slits. Sometimes the photons hit the screen and bounce off. Sometimes they go through the right slit, and sometimes they go through the left slit. So that's the complete experiment. As I said, just to review, when there's one slit's open, those occasional random photons that go through that particular slit that's open hit the photodetector directly behind the slit. If one or the other is open. When they're both open, something happens where those photons interfere with each other. And the initial experiment, you had the laser turned on high, and you could sit there and look at the photodetector, or if it was just a white screen, you could see, with the 2 slits open, you could see this striped pattern of an interference pattern, visually, real time. But if you turn that laser down and get one packet at a time, let's rerun this experiment and see what happens. The physicists wanted to see whether if you put one photon at a time at this target, and occasionally one goes through this slit and one goes through that slit, well, now there's not going to be any interaction between particles. Because, of course, when you're shooting all these particles randomly and at a very, very high rate, you might have one particle here that went through the right slit and is on the way to the target, and another particle here that went through the left slit and is on the way to the target, and maybe they're interacting with each other. So if we shoot one at a time, we will have no possibility of interaction between the 2 particles. That's the whole idea. Well, we ran the test, and what we found was, even if we're shooting one particle at a time, we still see an interference pattern emerge on the back wall. One particle at a time. Eventually, we see the pattern emerge after we get maybe a few hundred of these impacts. And yes, it's an interference pattern, not a particle pattern. That's weird. because these particles are interacting, but they have nothing to interact with. These experiments have been done in vacuums and in all different various kinds of test configurations where they've proven, although they have nothing to react with, they seem to be reacting or interacting with something to cause this interference pattern. Because remember, the whole definition of an interference pattern is that one thing is interfering with another thing and creating this pattern, right? Okay, so what they decided to do next was, let's put a detector on each one of these slits, and we're going to watch, and we're going to, there's lots and lots of ways to create detectors that can detect particles going through slits, and we're not going to get into how these things are built. We're just simply going to say that we could build an apparatus that could detect whether something went through this slit or that slit or no slit, right? If, let's say, each one of these detectors has a little green light on it, and when a particle goes through, it lights up the green light. Well, if we send a packet to go through one of the slits and neither one of those green lights goes on, that means the packet hit the screen. And then we send another one, no green light, must have hit the screen. Send a third one, the right light went on. That means it went through the right slit, right? And you run this test enough times, send enough packets, you're going to get a bunch of packets that have been shown to go through the one slit and a bunch of packets that have been shown to go through the other slit. The test results, remember, the only difference between the double slit experiment that has single packets randomly going through slits with no detectors on it, that shows an interference pattern. Once we put the detectors on there, we see a particle pattern. If the person running the test is sitting there keeping track of which slit the photon went through, all of a sudden they start behaving as a particle. What? So it seems like photons act as particles if you're watching, but they're not acting as particles if you're not watching, which, ridiculous, right? I mean, how would they possibly know that you're watching, right? I mean, this is really ridiculous. It was ridiculous enough that if there's only one slot, it acts as a particle, and if there's two slots, it starts acting as a wave. That's ridiculous enough. But now what we're saying is, if you actually try to figure out which slot they're going through, they stop acting as a wave altogether. They start acting as particles again. So hundreds and hundreds of different test setups have happened, lots and lots of theories, lots of discussion. What they've really discovered is that consciousness seems to be involved here, because here's what happens. If you take that setup where you've got the two green lights detecting whether or not the particles have gone through whichever slit they go through, some scientists are thinking, well, maybe what's going on here is that to be able to detect whether a particle went through that slit, we must have had to affect it in some way. And there's certainly a truth to that matter. Heisenberg sort of said this, well over 100 years ago, that to detect whether an object's basically, there's no way that you can detect an object's speed or position without affecting the object, is basically what he said. So scientists thought, well, okay, so our apparatus is too crude. We're affecting how these particles are behaving. Well, they came up with lots and lots and lots of different ways to sense the particle position, and I'm not going to get into any of that detail, except to say they ruled that out. We are not affecting the particle's position with those sensors. So how else can we check what's going on here? Well, they actually came up with a very, very simple approach. What they decided to do is, we are going to block, even though we've got sensors detecting which slot the particle went through, we're going to block those sensors from view so that the experimenter cannot see that information. That shouldn't make any difference, right? I mean, whatever's going on in that test apparatus, nothing changed. The only thing that changed is the fact that the person running the test couldn't see which of those lights went on. What we found from that experiment is more astounding than we've already discovered with the previous tests. And that is, if the person running the test, or any person whatsoever, if no person can see which of the slots the particle went through, it will act as a wave. As soon as anybody can see that information, it acts as a particle. Really. All it takes is a person to be able to see the information. And here's the theory, which is so far proven to be accurate. That what's going on here is consciousness is involved. And when the information enters consciousness, the photon acts as a particle. If that information, that location information, if that doesn't enter consciousness in some way, it is a wave. And there's only one sort of deeper layer to this, and that is this. So basically what the quantum mechanics, quantum theory is based on this whole behavior. And the way it turns out is this, is when a subatomic particle, if there's a subatomic particle like a photon, emitted from the sun or a light bulb or a laser beam, and it's on its way to a target, it does not have a position or a speed or a momentum or any physical characteristics until it is witnessed by a conscious observer. So what does that mean? Well, so it's in a state of what quantum physicists call superposition. Superposition means it exists everywhere and nowhere. It has a certain probability of existing in particular places, but it doesn't actually exist in that place until you collapse its superposition. So superposition is this odd thing that defines a particle that basically says it does not actually have a position. It doesn't have any characteristics whatsoever except the probability of being in a particular place and time. It's all probabilistic, which of course, that's why Einstein said God doesn't play dice with the universe, because he didn't want to believe that the universe really works in a probabilistic way. He assumed it worked in a deterministic way. Einstein would have assumed that if a particle went through a slit and it started behaving like a wave, some force must have acted on that particle to cause it to veer off from simply going straight to the back wall, because there's a whole Newtonian principle that says every action has an equal and opposite reaction, and a body in motion will remain in motion until acted upon by an outside force, right? These are some of the platitudes of Newtonian physics. Well, this whole idea violates all of that. So there's this thing called superposition that all subatomic particles have, where they don't actually have a position. They just have a probability of being in a position. And they don't actually devolve into an actual particle that we can give a position to until superposition is collapsed. And the way you collapse superposition is by witnessing the particle consciously. Right? If you have a machine that simply witnesses the particle and the information in that machine is thrown out, then that has not been witnessed. If you have a machine that witnesses a particle and that machine saves that information, and at some later time a human looks at that information, then it collapses at the time that the human looked at the information. So the human could look at that information a week after it was collected. That position didn't exist until the human looked at it, until it entered consciousness. That's how weird this stuff is. That's why Richard Feynman, who was really the father of quantum physics, who taught at Caltech in the 1960s and won the Nobel Prize in 1965, said the following about quantum theory. Anyone who is not shocked by quantum theory doesn't understand it. He also said, what I'm going to tell you, this is at a lecture he gave, what I'm going to tell you about is what we teach our physics students in the 3rd or 4th year of graduate school. This was back in the 60s when he said this. It is my task to convince you not to turn away because you don't understand it. You see, my physics students don't understand it. And that's because I don't understand it. Nobody does. All right? So, this is the father of quantum physics, basically saying, don't try to understand this because you won't. It's just too strange. As a matter of fact, another famous thing that he would tell his students when they would raise their hand and say, but I don't understand this. Basically what he would say is, and he actually had t-shirts made up that said this on the t-shirt, shut up and calculate, is basically what he said. Basically, it's don't try to understand why this works. You can understand Newtonian physics. You can picture it, you can model it in your head, and then you can solve equations and formulas to solve particular problems. Quantum mechanics is different. You cannot understand it. All you need to do is plug the numbers into the formulas, run the formulas, and you will get the correct answers. All right? So we've got this very, very odd thing going on. No one understands it to this day, but it actually is true. And what it involves is what we consider to be physical particles of matter that have no speed, no weight, no size, no location, until witnessed by a conscious being. And once that witnessed event enters consciousness, superposition is collapsed, and that particle will reveal its position. So that's why this interference pattern happens when only a single particle goes through one of those two slits. In fact, that particle is interfering with itself because that particle is going through both slits at the same time with a certain probability. That particle is actually located in every position in the universe simultaneously at some level of probability. Right? The probability that that particle is on the other side of the moon is incredibly small, but it is possible. The probability that that particle will go through either one of those two slits is reasonably good, and it's just as high a probability of going through the right slit as the left slit. So we'll actually go through both slits simultaneously at some probability. Let's just invent some numbers. Let's say it's got a 10% chance of going through the right slit, a 10% chance going through the left slit, and an 80% chance of just impacting that little screen with the two slits in it. So you got a 10% chance it'll be here, and a 10% chance it'll be there. You can kind of think of that as 10% of the particle is going through this slit, and 10% of the particle is going through the other slit simultaneously. And guess what? They are interacting with each other. And that's what causes the interference pattern on the back of that screen. Bizarre? Absolutely. It's the way quantum mechanics works. All right? The reason that makes a difference is, the way it impacts you is two ways. First of all, it should give you a sense of how the world works and how odd the world is. And I wanted to show you that the world is not what you think it is. And reality is not what you think it is. It does not work the way you think. Very, very strange things happen in reality. But you don't see those strange things very often. And you especially don't see quantum superposition that easily because it only happens to very small objects, right? This pair of scissors is made up of trillions of subatomic particles. And those subatomic particles have various probabilities of existing and not existing. Right now, as you look at this pair of scissors, various of these particles that comprise these scissors are on the other side of the moon, are under the table, or on the other side of the universe. They blink in and out of existence. Well, why don't you see this thing blinking in and out of existence? Because there's trillions of them. And the probability is that each one of these particles, the highest probability of its existence is being exactly where it is right now, right? It does have a probability of being located somewhere else, but it's a relatively small one. And there is a chance, if we were to be able to wait an infinite length of time, It will occur that these scissors will not be right here in front of me, not between my fingers. All of the particles in these scissors, probabilistically, will end up being somewhere else, all at the same time, if I wait long enough. The problem is, that's a very, very long time for me to wait, so I'm not going to bother. So the point is, when we're living our lives, we really don't see these quantum effects happen very, very well. With the exception that there are certain devices in our world that rely on quantum properties to work. There's a whole principle called quantum tunneling or electron tunneling that are behind certain kinds of semiconductors, certain kinds of diodes, certain kinds of transistors. You wouldn't be able to be, using your cell phone if quantum mechanics wasn't at play, because quantum mechanics helps that cell phone work or any electronics work. The scanning electron microscope, it works. It's actually the correct full name for a scanning electron microscope is a scanning tunneling electron microscope, and it relies on this tunneling principle. All right. So the other thing I guess I would say quickly, and then I want to give you another example of how this tunneling works, is that for the principles that we're talking about with the double slit experiment and particles versus wave behavior, that requires these events to enter consciousness to have an effect, because superposition needs to be broken. The tunneling aspect of how quantum mechanics works is really kind of a different behavior of quantum mechanics. We don't actually have to have a person seeing each one of these electrons, doing its tunneling for it to actually happen. So these are different attributes of quantum mechanics. I'm really kind of mixing and matching these two things. And you know what, I'm not going to even talk more about tunneling at this point, because I think it'll only serve to confuse. Just remember that particles that are very small, until they are witnessed, don't have a position. They are in superposition. And once they are witnessed, they enter consciousness, and that process causes superposition to collapse. And in that case, they reveal their position. That's the long and the short of it. There are lots of YouTube videos that fully describe this process, and I would invite you to take a look at a couple of them, just so you can visually see. It's a little easier to demonstrate in a video than it is these little scraps of paper that I have. So what's the net of all this? The net of all this, as I just said, is the world is stranger than you think. I've given you multiple examples in the last few units of strange things like, creating limbs that aren't there. The fact that you create your own visual scene. You actually create the world and visually what it looks like. You create that within yourself, and you even create some aspects of your own reality within yourself. As I said, with things like false limbs. You can even change physical things in the world, like whether a ball drops into a particular location in that ball drop experiment or it moves to another location. You can know that things are going to happen, like 9/11, before they happen. And everybody knew it to some degree, because they changed computers running random number generation software throughout the world. So all of these are examples of the kind of impact that you have in your world, and they really hopefully are giving you an appreciation for the fact that at some level you are weaved very, very tightly into the world that you're in, and you're not just a lump of living cells walking around a planet in a physical universe. It's a bit more complicated than that. All right? So what I'm going to get to next in Unit 7 is reincarnation and mediumship. And now we get into some really fun stuff, because this is completely non-scientific in terms of, well, historically. Historically, science has poo-pooed any of this stuff, and even today, generally it does. Although there's very smart people who have graduated from very good schools who have really discovered amazing things about these different kinds of behaviors. And we're going to talk about a bunch of examples, and maybe even talk about how these sorts of things might happen. But that's next time. Take care.